Okay, today we're going to look at section 2.2, and in this lesson we're going to be beginning to step into the idea of proof. So we're going to start with some properties from algebra and then build into geometry proofs. In algebra, there are certain things we're allowed to do in an equation as long as we do them to both sides. So we could add 4 to both sides of an equation, for example. But in geometry, we're going to step that, instead of just saying we can add the same thing to both sides, we're going to say we can add equal things to both sides, because sometimes in geometry we might be talking about equal segments. So as long as they're equal, we can add different segments as long as the size is the same to two sides of an equation. So we can add, we can subtract, we can multiply, and we can divide as long as we're adding or subtracting or multiplying, dividing by equal things. And we're not allowed to divide by 0 because that's like the biggest no-no in math. So those are our addition, subtraction, multiplication, and division properties. Our substitution property says that if two things have the exact same value, we can use them interchangeably. We can plug one in for the other, and that may help us solve certain problems. Our reflexive property seems like kind of a silly one because it just says A equals A. So obviously something is equal to itself, so it seems a little bit ridiculous, but we actually will use it a lot. Our symmetric property says that equations work forward or backwards. So just like x equals 3 or 3 equals x. Transitive property is a favorite for geometry students. Once we learn it, this is kind of a go-to and we use it a lot. It says that if A is equal to B and B is equal to C, then A is equal to C. So in that transitive property, what we do is we kind of set up a chain and we say I can get from A to B, I can get from B to C, so that must mean that A is equal to C. We're going to apply some of these properties in solving an algebra problem, but we're going to show every step of our work and we're going to justify each step, which means that we are going to give a reason for why we're allowed to do something. So our first step in solving this algebra problem would be to get all the x's together by adding 1/2 x to both sides. So what we're going to do is write 1/2 x equals 1/2 x. That's a true statement, and so there we're going to say that's our reflexive because two things are exactly equal to each other. Next to that first step, we actually should write that it's our given. Our starting equation is our given piece of information. Then we're going to take that 1/2 x and we're going to add it to both sides. So I'm going to have 3½ x equals 6. And our reason for being able to do that is that additive property of equality, that we're allowed to add the same thing or equal things to two sides of an equation. So our next step, if we're trying to get x alone, is to divide by 3½ So we're going to say 3½ equals 3½, which would once again be reflexive. Whenever something equals itself, that's our reflexive, just like a mirror reflects back itself. And then we're going to divide both sides by that 3½. So that gives us x equals, and 6 divided by 3½, we can do on a calculator or by some arithmetic and get 12/7. What we did there was our division property of equality. We divided both sides of the equation. So that's how we work our way step by step through an algebra problem, making sure to show every step of our work, which might be really painful for some of you, but we need to show every step and we need to say why we're allowed to do that step. In geometry, a lot of times we aren't as concerned with the final answer as the process along the way. And so we have to show every step and say why we're allowed to do what we're doing. So now we're going to take that same idea, but bring it into a geometry problem. So in this, we are given some information, and we're going to mark our picture accordingly. So we're given that RT and PQ are intersecting at S, so that RS equals PS, so we can mark those as being equal, and ST is equal to SQ. And what we want to prove is that the whole of RT is equal to the whole of PQ. So in geometry, when we set up a proof, we're going to use two columns. In one column, we're going to write our stuff or our steps, and in the other column, we're going to write our reasons or why we're allowed to do what we're doing. A good place to start, always when in doubt, is to start with our givens. So we're going to say RS equals PS and ST equals SQ. And that's our given information. Almost always we're going to start with givens. Not always, but almost always we'll start with our givens. Now we have two equal statements here, and so we can apply any of those properties that we talked about at the beginning, the addition, subtraction, multiplication, or division. So what we're going to do, since we're trying to put together segments, is we're going to add those pieces together. So what I'm going to do is take the left sides and add them together. So say RS plus ST, and I'm going to take the right sides and add them together and say that's equal to PS plus SQ. So adding together the lefts and adding together the rights. And the reason we can do that is the addition property of equality. So now for our third step, what we're going to do is say, okay, now if I look at the picture, how can we put some pieces together here? There's 4 different pieces in the picture. We want to finish only talking about 2 different pieces, so how can I put some stuff together? So I'm going to say RS plus ST, just looking at the picture, would have to be equal to RT. Putting together 2 small pieces gives us a bigger one. And likewise, putting together, we can say that PS plus SQ is equal to PQ. And that is something that we learned way back in chapter 1. I think it was section 2 or section 3, but it was called our segment addition postulate. That segment addition postulate says that we are allowed to add together pieces of segments to make bigger segments. So that segment addition postulate is going to be kind of a big deal for us that we're going to use a lot. Now our final step is going to be to look at our last 2 previous steps here and combine some information. So what I can do is look at step 2 and say, that says RS plus ST, but this next step also says RS plus ST is the same thing as RT. So what I'm going to do is plug an RT in there and say RT equals, and then we have a PS plus SQ, but that shows up again as being equal to PQ. So I'm going to plug that in there. So then I have RT equals PQ, just like we wanted. So what we did there was plugging things in for other pieces. So we did a substitution. A substitution is where we rename pieces or where we plug pieces in for other ones. So this proof was 4 steps. Our proofs for now are probably going to be about 3 to 5 steps. We almost always are going to start with the given, and then we're going to progress on through our logic, and your final step, whatever that final last thing is in our list of steps, should always be whatever we're trying to prove. That's our destination. So our given is where we're starting the problem. Our proof is our destination, or where we need to end the problem. And we're going to make logical steps along the way until we can get there. Now, if you're feeling overwhelmed, like you're not going to be able to do this on your own, that's okay. In your homework, your problems are going to be fill in the blanks with proofs. So we'll do some examples that are fill in the blanks at the end of the lesson as well, so you can see how those work. But we're starting here with blank papers so that we can develop the logic and work our way up to these. So we'll do another example like this. We are given that angle AOC is equal to angle BOD, and we want to prove that angle 1 is equal to angle 3. Angle 1 is just that AOB part, and angle 3 is just the COD part. So, once again, a good place to start a problem is with our given. So we're going to start with the measure of angle AOC being equal to the measure of angle BOD. Then when I look at AOC in the picture, AOC is made up of two different pieces, so I'm going to break it down and say the measure of angle AOC is the measure of angle 1 and also the measure of angle BOC. And likewise, when I look at the picture, BOD is the measure of angle 3 plus the measure of angle BOC. So we're looking at our given angles and what makes them up and trying to break them down into their smaller parts. What we're doing there, we learned back in chapter 1 as well, and that was our angle addition postulate. I think that was section 1.4, where we learned that angle addition postulate, that we can add together angles that are next to or adjacent to each other and make them into a bigger angle. So now what we're going to do is say, well, we're kind of repeating ourselves a little bit here. We talked about AOC, we talk about AOC again, so we're going to take its new name and replace it. And likewise, we talked about BOD, we talked about BOD again. We're going to take that and replace it. So what we're going to do in step 3 is rewrite step 1, except we're going to use the step 2 names. So we're going to say measure angle 1 plus measure of angle BOC is equal to, instead of BOD, the measure of angle 3 plus the measure of angle BOC. Rewriting step 1, but using the names from step 2. So since it's a rewriting by plugging in new things, that's our substitution property. So now if we keep in mind our destination and what we're trying to prove, we're trying to prove that angle 1 is equal to angle 3. So I feel really good about step 3 because I've got 1 on one side, I've got 3 on the other side, so we're pretty close, but we've got those BOCs in the way. So one thing we know about BOC for sure is that it's at least equal to itself. If nothing else, we can always say something is equal to itself. And that property is our reflexive property. It reflects it like a mirror, that something is always equal to itself. So now if I think about steps 3 and 4 like an algebra problem, if I want to get rid of that BOC on both sides, I would do so by subtracting it. If I subtract that off of both sides of the equation, we're left with exactly what we want. So that is our subtraction property of equality. Okay? Now these last groups of problems are going to be more similar to things that you're going to see on your homework. So what we want to do here is justify each of these using one of our properties of congruence. So the first one, when something is equal to itself, that's called our reflexive property. Feel free to abbreviate as long as you're using enough of an abbreviation that I can tell what you mean. And the next one, if AB is the same as CD, which is the same as EF, then AB has to equal EF. That's our transitive property, that we can step by step make it from one piece to another piece through equalities or through congruences. So we're setting up a chain of equality. And the third one, if RS is equal to TW, then TW equals RS. They say exactly the same thing, but they say it backwards. That's our symmetric property. In the next one, we want to think of this as an algebraic equation and what we would do to solve it. So if x plus 5 equals 16, then x is equal to 11. How? How is x equal to 11? What would we have done to solve it? Well, to get the x alone, we would need to subtract from both sides. So that's our subtraction property of equality. Now this next one's a little bit of a tricky one because it actually wasn't listed out at the beginning of the assignment in the steps, but we did use it already this year in some homework assignments, and you learned it in Algebra 1. It's where we want to take the 2 and pass it out through the parentheses, multiplying by each thing, and that's called our distributive property. Now in this last one, we're told 2x plus y is 70, and y is the same thing as 3x. So 2x plus 3x is 70. So what we want to do is look at what changed. So if we look at the starting one and the ending one, we want to say what's different about it. Well, a y turned into a 3x, which we can do because y is equal to 3x. So what we've done is we've taken the y and we've exchanged it for a 3x. So when we exchange or rename part of a problem, that is our substitution property. So in your homework, you'll be asked to justify certain statements like these. And so we have that list at the beginning of the notes here today that you can use for justifications. In your homework, all of your proofs are going to be fill-in-the-blank proofs. So they could look something like this. Sometimes you might have to fill in statements. Sometimes you'll have to fill in reasons. But some of the proof will be there for you, so you don't have to do the entire thing on your own yet. So usually, almost always, the first reason is going to be given, that it's a really good idea to verify that. So when I look at what it says in that first line, I want to make sure that that actually is the given up in the original problem. So angle 1 equals angle 3, angle 2 equals angle 4. That is what the given says. So that first reason is given. Now, we have to ask ourselves, so how do we make this next step? So as we move from step 1 to step 2, what have they done? Well, we added together 1 and 2, which were both on the left side, and we added together 3 and 4, which were both on the right side. So we have to say what tells us that we can add together lefts and add together rights of equations. And that's our addition property of equality. Then to move to step 3, we have to say, okay, well, what's going on there? Now we're starting to bring in letters, and there were no letters in the problem yet, so this must be referring to the picture. So if we look up at the picture, angle 1 plus angle 2 is angle ABC, and we can see that happening in that left-hand portion of the picture. Angle 3 plus angle 4 is angle DEF, and we can see that happening there in that right-hand portion of the picture. So what's happening is that we're adding together angle pieces to make bigger angles. So that's called our angle addition postulate that we learned back in chapter 1. So then just like our first step has to be the given, the last statement on the statement side where we're going through our steps has to be what we're trying to prove. That's our destination. But the reason will never be the word prove. Students always want to do that because we write given for the first one, so they want to write prove for the last one. But that will never be the right word. So we have to think about what one of our properties or postulates allows us to move from our steps to saying that final destination. So as we combine what we have in steps 2 and step 3 here, in step 2, we have angle 1 plus angle 2, and we say that again in step 3, but we now call it ABC. So we're going to plug that in. In step 2, we have a 3 and 4. In step 3, we have a 3 and 4, but we give it a new name of DEF. So we're going to plug that in and say that ABC is equal to DEF. So we're rewriting step 2, but we're switching out from number names to letter names. So when we're rewriting but switching out names, that is our substitution property. So in your assignment for your homework, your problems will be similar to this, where you'll be given some of your statements. Sometimes you'll actually be given some of the reasons as well. But we work through trying to follow their logic and figure out how do they move from one step to the next step. So we'll do another example like this together, and then you'll be on to your homework. So we have a picture, we have some given information, and we have our destination. That stuff will always be there for you. The given, what you're supposed to prove, and then often there will be some sort of a diagram that gives you your information as well. So almost always the first reason is given. Not always, but almost always. So as I look for ST equals RN, it is right there in the given, so our first reason is going to be given. Now we have some blanks on the statement side. So it says blank is equal to SI plus IT. If we look at the picture and go from SI plus IT all together, that makes up ST. And likewise, if I go from RU and UN and put that together, it makes up RN. So what do we call it when we're adding together smaller segments to make bigger segments? We learned that back in chapter 1. That is our segment addition postulate. So then we have to ask ourselves, how did they get from steps 1 and 2 to move on forward to step 3? So we have an ST in step 1, we have an ST in step 2, but we renamed it. Then we have an RN in step 1, we have an RN in step 2, but we renamed it. So step 3 is step 1 written all over again, except ST became its longer name and RN became its longer name. So when we're renaming, whether it's for shorter names or longer names, anytime we're plugging pieces in for another one, that's our substitution property. IT equals RU. That seems kind of like a random piece of information. If we look at the picture, they're marked as being equal, but we can't refer to a picture in our reasons. But if we look on up at the top, we actually didn't use our entire given before. They held off on that piece of information until later. So that is actually given information again. The final blank on the statement side always, always must be what you're trying to prove. So SI equals UN is what we're trying to prove. So we have to ask ourselves, then how do we get there? If we combine the logic of steps 3 and 4 and think about them like an algebra problem, how would I get rid of that IT and RU? I would subtract them. So this is going to be our subtraction property of equality. For your homework from section 2.2, you're going to do 1, 4, and 6 through 10, and then you're going to choose to do either 12 or 14. 12 and 14 are not fill-in-the-blank proofs, so it's just a blank piece of paper proof like our first 2 problems that we did. Don't worry about them. Don't stress about them. I want you to try one of them and do your best with it. I just want to see where you're at. Some people click with the idea of proof faster than others, so I just want to see if there's anybody that's really clicking with it yet. If you're struggling, that's okay. Don't worry too much about 12 or 14. Just give them a shot. You know how to start. We can always start with a given, and you know where you're supposed to end. And then just see if you can figure out a couple of steps in the middle that might help you get there.